All right. As we're giving folks a couple of minutes to come back in, we're going to begin with our next and final speaker for this session of Cosmic Noon, which is, who is Xiangyu Jin, who will be giving us a talk about charting the late stages of reionization with JWST NearCam WFSS.
Yeah. Hi, everyone. Can everyone hear me okay? Okay. My name is Xiangyu Jin. I'm currently a postdoc at the University of Michigan. So I know we are in the Cosmic Noons session, but we're going to travel back to Cosmic Dawn to talk about cosmic reionization. And today, I'm going to talk about a few work we did with JWST NearCam wide field spectroscopy to study the cosmic reionization. And I would like to thank the organizer for giving me this chance to talk about this study. So at first, I want to briefly talk about cosmic reionization. Cosmic reionization is basically a phase transition that connects the neutral IgM to the fully ionized IgM we are seeing today. So it encodes a lot of important information of those first UV luminous sources in our universe. With intense studies over the past 2 decades, so here I'm leaving a lot of those progress on the timeline of cosmic reionization. So this is IgM neutral fraction as function of redshift. So I'm showing the measurement from quasar in those blue data points and measurement from galaxy in those yellow data points. So as you can see here, the cosmic reionization has a sort of like extended timeline. And it starts greater than redshift 10. And has a middle point about redshift 7 to 8, but you can see it shows a very large scatter in the IgM neutral fraction. And the timeline is pretty extended. It's also and below redshift 6, even redshift 5.5. So in this talk, I'm more focused on this end of reionization below redshift 6.5. I'm going to talk about a few work we did to probe this cosmic reionization with JWST NearCam wide field spectroscopy and in quasar field, also black field. And there's 2 main questions we study with those observations. One is the topology of reionization, how did reionization happen? And the second question is what drove reionization, the dominant source of reionization. So because we're probing cosmic reionization, I think it's very important to introduce quasar lemma forest. This is a series of absorption line bluers of the lemma alpha emission. So when the light from the quasar passes through the integer median, if there's a neutral cloud with neutral fraction greater than 0.1%, it will cause complete absorption in the quasar lemma alpha forest or 0 transmission in lemma forest. But instead for those highly ionized region, the light just passes through the integer median, and you can see pretty high transmission in the quasar lemma forest. So with this quasar lemma forest, is a pretty efficient probe of those ionization state of those diffuse gas in the integrated space. So we know reionization probably ends below redshift 6. But during this ending stage of reionization, the IgM was still undergoing a very rapid change. First, you can see the result from the ionizing photon mean free path measurement from redshift 5 to redshift 6. It drops almost by 1 order of magnitude. Meanwhile, if you measure this effective optical depth of quasar lemma alpha forest, what you can see here is that the quasar lemma alpha forest, its optical depth increase very rapidly from redshift 5 to redshift 6, and also display a very large scatter, indicating there is some large scatter in the IgM transmission at the end of reionization. And there are a few models propose different topology of reionization to explain this large-scale fluctuation in the IgM transmission. So here I'm showing the model prediction from 2 models. I'll show one snapshot and the other snapshot later. Those color dots are indicating galaxy with different UV luminosity, and the IgM transmission is color-coded. So a lighter color indicates high IgM transmission or low IgM effective optical depths. So in this model, that this large-scale fluctuation in transmission is driven by the fluctuation in the ionizing background. Near those overdensity of galaxy, you expected to see more transparent IgM because they have more ionizing photon. But in a competing model, that when this large-scale fluctuation in IgM transmission is actually driven by the fluctuation in the IgM temperature. Near those overdense region of galaxies, instead you are expected to see a lower lower IgM transmission because those overdense region of galaxy get ionized earlier. So they have longer time to cool. So actually the transmission near them is very, very low. So we want to study this topology of ionization using quasar and also the just near can wide field through the spectroscopy observation. So the data we are using is from the Aspire program. Figure already gave an introduction of this program earlier this morning. So it's basically a near cam CLIS program targeting a 25 quasar field with just single near cam pointing. And this mode is like very efficient. So we identify around 500 O3 emitting galaxies in this 25 quasar field with just single near cam pointing. And there's some overdensity of O3 emitter at the quasar redshift, and figure demo will tell you about how exciting this thing could be. And I will focus more on those O3 emitter in the quasar foreground within the redshift range of the quasar lemma forest. And the approach we're used to constrain this topology of ionization, or how do we measure this IgM transmission near those O3 emitter, is that we put a sphere shown by this green sphere, and those O3 emitter detected in the quasar field shown by the little green dots by their redshift, and the transverse distance between the O3 emitter and quasar. And the quasar lemma forest is shown by this black line. So we put this sphere, and this sphere has a radius which we call influence radius. If this sphere encloses part of the quasar lemma forest, then we think this O3 emitter is impacting the lemma forest. But for this part of lemma forest, we don't detect any O3 emitter. Then we think that O3 emitter are not impacting the quasar lemma forest. So we have 14 quasar set line with this existing ground-based spectroscopy to do this analysis. So here I'm showing the stack lemma forest of this 14 quasar set line that is near the O3 emitter on the top and away from the O3 emitter, means that those lemma forest is not enclosed by any sphere of O3 emitter. So very obvious things is that if you see the redshift about redshift 5.7, you can find most of the transmission spike in lemma forest actually around the O3 emitter. And away from the O3 emitter, you only get a pretty dark trough. And below redshift 5.7, there are a bunch of transmission spikes near the O3 emitter. There are also some spikes near the O3 emitter. I forgot to mention, this is the stack result when we use the influence radius 25 co-parsec. So this is a very large scale. And then we measure the optical depth of these two stack spectra separately. So what we can find here is that at the same redshift, the IgM effective optical depth near the O3 emitter is much lower, indicating the IgM transmission is much higher near the O3 emitter when we adopting this influence radius 25 co-parsec. So there's some excess transmission near the O3 emitter. And what's more exciting is that if we trying to match the same effective optical depths, we find those regions near the O3 emitter reach the same optical depth at least 0.1 in redshift ahead of those regions away from the O3 emitter. And this indicating the reionization process actually happened earlier near those O3 emitters. So this is consistent with an inside-out topology of reionization, and this is also consistent with the model that assuming this large-scale fluctuation in IgM transmission is dominant by the fluctuating UV background model. So after we seen this large-scale axis transmission around the O3 emitter, how do we know like the exact distribution of IgM transmission near the O3 emitter? To do that, we need a much deeper lemma alpha forest spectroscopy, and we can do a cross-correlation function between the quasar lemma alpha forest and those spatial location of those O3 emitter. And this work is done by Koki Kahichi. So we are using 5 Aspire quasar field with very deep ground-based lemma alpha spectroscopy. The cross-correlation function between the lemma forest and the O3 emitter shown by this black line. And we also generate a random cross-correlation function by those red data points. So this is tracing the average IgM transmission at this redshift. So what you can see here is that compare with the random cross-correlation function within about 5 to 10 co-parsec, the IgM transmission is actually lower near those O3 emitter. It's indicating there's some gas overdensity near those O3 emitter. But if we move to larger scale, about 20 to 50 km/parsec, we can see, compare with the random IGM galaxy cross-correlation function, we're seeing this strong axis transmission in this cross-correlation function. This is very exciting because it's indicating those regions traced by the oscillatory emitter must contribute to reionization. So we can see axis IGM transmission near those oscillatory emitter. And we model this scale and the amplitude of this axis transmission. We find that the observed oscillatory emitter alone cannot produce this strong axis transmission near the oscillatory emitter because the scales appear like 20 km/parsec, even with 100% escaping fraction. So it means that those pure bright oscillatory emitter cannot drive the reionization alone. So there must be some contribution from faint undetected galaxy cluster around those bright oscillatory emitter to ionizing background during reionization. So we are able to do this with more data. So here I'm talking about cycle 2 program GO3325. I forgot to include an introduction slide for this. It's also PI by Figure here, also Jin Yang at University of Michigan. So we target a 2 of aspire quasar field with a larger near-cam pointing, and also near-spec observation. So this plot is showing the footprint of those near-cam observation and the near-spec observation. So near-cam pointing is by this blue, purple and green shaded region. And for most of the region, we have near-spec coverage shown by those yellow shaded region. So with near-spec, we're able to have a wider wavelength coverage than those near-cam Grism, because with Grism, we're only able to see H-beta and oscillatory emission line for redshift 6 galaxy. But with near-spec, we're also able to see H-alpha and even nitrogen 2 if they are very bright. So we put most of the oscillatory emitter, we set it from Grism into the near-spec observation. We confirm like 80 of those out of 82 bright Grism set oscillatory emitter are really star-forming galaxy at that redshift. And we also put some like fainter Grism set oscillatory emitter. By fainter, I mean that they only have line detection in either 1D or 2D. And we confirm 20 more fainter oscillatory emitter, Grism set oscillatory emitter actually star-forming galaxy in the about redshift 5. So here I'm showing a comparison between Aspire with single near-cam pointing result and 6 near-cam pointing result in near-spec observation. So you can see we find a lot of more galaxy in this quasar field, and there's indeed like some spatial correlation between those galaxy over density structure and quasar lamella forest. For example, when the galaxy get really close to quasar lamella forest, we only see absorption. And when the galaxy gets slightly further from the lamella forest and there's a galaxy over density, we see very strong transmission spikes in the quasar lamella forest. So we measure this cross-correlation function just using this single field, and this cross-correlation function is shown by these red data points. When we compare with the cross-correlation function from Koki's result shown by those black data points, we find they're more or less consistent with each other. Although the scale, it could be slightly different in the axis transmission could appear like closer to the galaxy in our single field measurement. But when we compare with the measurement from other GLST study from Cascino et al. 2025, that's Eiger result, and Zhu et al. 2026, I think, from another 2 quasar field, we find this IGM galaxy cross-correlation function actually could appear everywhere. So it's like a pretty large cosmic variance. And this large cosmic variance is actually predicted by the season simulation. So this is the simulated IGM galaxy cross-correlation function using different number of quasars. So on top is only showing 1 quasar, and those color lines is the single quasar cross-correlation function. And this figure shows the 50 quasar IGM galaxy cross-correlation function. So as you can see here, the cosmic variance basically causes a very large scatter from 1 quasar. And this cosmic variance is kind of shrink when you have large number of quasars that's fine. So we definitely need a much large number of quasars that's line with near-cam Grism observation to measure this cross-correlation function well and reduce this large cosmic variance. And as I mentioned, we have near-spec data in this program. So we are able to identify some broad H-alpha emitter among those GRISM set all 3 emitters. So one example is shown here. So we identify 4 of those broadline H-alpha emitters. They're shown by those little red dots here. And if you zoom in the quasi-lemma forest near those broadline H-alpha emitter, within a very small scale, like 5 commilliparsec, you're always able to find some transmission spikes near those broadline AGN. So we measure this cross-correlation function with just 4 objects. So this is AGN cross-correlation function. So by compare with this AGN cross-correlation function in red with this IGM galaxy cross-correlation function shown in blue, we can find there probably looks very similar except for small scales, like within 5 commilliparsec, there is a peak in the IGM transmission. And this peak, if this is really caused by those broadline AGN, we model this transmission, it will indicating the ionizing photon production rate escape from the AGN is very, very high. It's probably indicating 50 to 100% ionizing photon escape fraction. But as you can see here, the IGM AGN cross-correlation functions with only 4 objects also show a pretty large scatter. So we need a large sample of AGN in the quasar field to do this analysis and confirm whether we can really see this axis transmission appear as very small scale, very close to the AGN. And I hope I have time to talk about Cosmos 3D. So Cosmos 3D, as Bin Chen Figure has introduced earlier today, is a pretty large near-time GRISM survey in a single field in the F44W GRISM. So we're able to set a very large sample of galaxies with Cosmos 3D. I don't have too much detail to go through like how do we set H-alpha emitter in Cosmos 3D, but feel free to ask me after the talk. So we basically set almost 1,400 H-alpha emitter candidates from Cosmos 3D survey. So it's shown by all the 1D spectra shown by this figure. So we on the figure on the left showing the photometric redshift and spectroscopy redshift of this H-alpha emitter sample, and we set those H-alpha emitter that has photo Z and spec Z relatively close to each other in our analysis, and we measure this ionizing photon production efficiency as function of the UV magnitude. And what we can find here is that this showing a very strong correlation between the psi and the UV magnitude. After we run in a CD feeding correct for the depth extinction, we find this trend becomes slightly flatter, but we can also find a correlation between the psi and UV magnitude, indicating those fainter galaxy in the UV is more efficient producing those ionizing photons. So I'm currently wrapping up the paper, so please stay tuned for the result. So as I want to talk about the future of this study, because we know the quasi-lemma forest absorption basically saturated at redshift 6.5. So if we really want to investigate early stage of cosmic reionization, we definitely need galaxy lemma alpha emission. And in cycle 5, we have 2 near-spec follow-up program that doing the follow-up of Cosmos 3D source, and we are able to get quick galaxy lemma alpha emission from these 2 programs. One is led by Roman Meyer, the other is led by Bin Chen Jin here. So we're able to study the topology of reionization by using these 2 programs. And because we are currently just within a week before Roman launch, so I'm also very excited about using Roman GRISM to study the topology of reionization. We have an analysis program in cycle 1 to do this. And I'll leave my conclusion slides here. And thank you very much for listening. Happy to take any question.
All right, so we do have maybe time for one really quick question.
Can you say a little bit more how you did the dust correction?
So it's basically we just run the I think Bin Chen did the SE feeding. So the basic procedure was like we run the backpipes SE feeding using the broadband photometry we have from I think Cosmos 3D imaging and also Cosmos Web imaging. And we consider like we have one H-alpha emission line from GRISM and use that information to derive the dust extinction and then apply the dust extinction to both UV continuum and H-alpha luminosity.
Any other questions? Okay. All right. Let's give Xiangyu another round of applause.
Thank you.
All right. So those are actually the end of our science talks today. Next, we'll be having a tutorial demo from Russell regarding the slitless utils package.
Do you hear me online, Gary? The bell. All right, thanks everyone. Thanks to Andrea, the rest of the LOC and the SOC for putting on this great workshop. You know, I've organized a number of these things for Roman, and this is a tremendous amount of work. So a hearty thank you to all of them for putting this on. But so we've heard a lot of really great science talks from the types of research that one can obtain from these types of data. And so I think we've also wanted to break these workshops up to also have more hands-on demonstrations and sort of pedagogy through the techniques. So I'm the first up to give that sort of shift of gears type talk. So we in STSCI have been creating a new suite of software to do analysis of solar spectroscopy. At present, it's only for HST, but you know, talk to me at the end if you've got another telescope in mind that's not named HST. But we were calling the package Solar Utils sort of an analogy to things you probably know, like photutils or specutils and so on. So that's sort of riffing off the same idea. And it's meant to ultimately replace things like AXI, if you're familiar with AXI. AXI is written in this sort of menagerie of C and Python. And so this is meaning to sort of bring it all into a coherent framework for modern interpretations of these things. So I'll just go ahead and leave this up for a moment. Along the way through the talks here, you're going to see these brown bubbles on the right. These are meant as little code snippets that you can run and do. I will post these slides on the Slack channel, so you know, don't feel that you got to run and grab this stuff. I will say that there is I started a Slack channel in the what's it called? The demos? I don't know. There's a thing called Solar Utils where I put the Jupyter notebook that I'm actually going to go through here as well. So you can grab that Jupyter notebook and go through it in real time with me if you want. But yeah, so that's how you can install the code. It currently uses Python 3.12 and a few other things. And so this will get you the bare bones stuff that you can run the notebook, either in these little examples that I've got here along the way, or when we get to the real notebook. I will say again, remember this is meant to work for WIFC or for WIFC3 and ACS. So when all of the examples that I'll be talking about today are actually packaged in the code itself. So in the solusutils.examples sub-package, you'll find all these things that go through different type of use cases that I think average person might want to deal with. So I want to start with just a very brief primer on solar spectroscopy. I mean, I know everyone here is interested in this, but I think it's important to talk on some of these things because this is going to, yeah. Did I have it upside down? Is that better on TV? Oh. Gary's motioning it is better. Okay. All right. Sorry about that, TV land. Yeah, so I want to go through a few pedagogical things just because that sets up the choices that you're going to see downstream in the code, and it'll make you understand. Hopefully, it will give you a better understanding. So I don't think anyone here needs explanation on why we want to do solar spectroscopy, but I think one thing that's always worth coming back to, I think Jen talked about this before or right after lunch, that a significant term in the spectral resolution budget is really coming from the sources themselves. right? And so you can think of this in analogy to when you did long slit spectroscopy in grade school, where the slit width kind of sets some overarching property of the spectral resolution. Really narrow slits give you really high resolution, but low throughput. And so this is really now the continuous limit that the slit goes to infinity. And so now the relevant size scale is something about the source itself. So something like the source is going to feed into the line spread function, or the effective line spread function that you get. And I always like to say, maybe you all can't see it at the very bottom, we all know the power of this, so I'm not going to go into that. But with great power comes great problems, and so the contamination is the dominant problem. It's the tall pole that everyone's trying to solve here. So I'm going to present a couple of different techniques that have been developed both for slitless utils and in the community to address the contamination problem. Many of the practitioners in the room probably are more familiar with these than even I. So if I say something, please don't jump out at me. So I want to talk about really fast how the data are handled inside of the code and how you should really be thinking of this. So over here on the left, in the bottom left, is what I'm imagining as the direct image. This is what you would see if you looked at it through any canonical filter that we've all seen and loved. And I'm going to build up from this simple picture, build up what the sort of equivalent dispersed image would look like. And this is just an example for ACS, but it really doesn't matter which telescope, camera, or grating we're talking about. But pedagogically, what we do is we have to take a position from the direct image and map it onto an equivalent position in the GRISM image. And this is typically done using the WCS, and we'll see in the examples why the WCS is really important for a moment. It's done by we have to then map that new position onto wavelength. It's some complicated polynomial. Most people don't need to worry about this. But once you've got the polynomial, you can then take a given spot from the direct image and then project it as a function of wavelength onto the GRISM image. And so cartoon, that's sort of shown here as little squares and rectangles that have a rainbow color palette associated with them. So you can see where, say, the bluest light would, say, fall in like this pixel here, whereas the reddest light would fall down there at the end. And to first order, what we have to do, when you hear all this talk about forward modeling and all these other things, what we're doing here is we're starting from this pixel, mapping it through as a function of wavelength, and then iterating over all pixels, and then building up some continuous mapping from the direct image scene to the dispersed image scene as a function of wavelength. And so inside of slitless utils, when it does this mapping, it then saves this mapping onto disk in the form of what I'm calling pixel dispersion tables. And so they tell you how an input position, x and y, here in the first two columns, and a wavelength, which for the moment is just described as an integer, but you should be thinking of this as a continuous variable, how x, y, and wavelength then map on to some output pixel here with some corresponding weight, and that's what the value is. So this is saying that input pixel x naught, y naught maps to all of these output x and y pixels at all of these wavelengths with all of this sort of geometry that maps onto it. And so you can see this is really just a geometric thing, right? Once you have specified where the telescope is going to observe, this table becomes immutable. Right? This is just simply encapsulating the geometry of the scene plus the optics of the instrument. And this is something that we can now use for downstream analysis. So the code is going to do all of this, this tabulation, behind the scenes for you and write off these things as HDF5 files that you can then do a bunch of things with. So what are the things that you could do? Well, the typical workflow is this here listed on the left. I should note that all of the code, all of the components, the APIs and whatnot, they're all documented in read the docs, and you can grab that here. And so I'm going to go through these things to some level in the notebook. I want to skip all of the primer stuff and just jump down to the extraction, because I think that's what most people here are interested in. So we've got two forms of spectral extraction. Something that you can think of as single. This is equivalent to what's in AXI. This is equivalent to the Horn algorithm, if you're familiar with the Horn paper. That's what you would do if you had just a single exposure. And then there's something that we call the multi-exposure. This is what I developed as the linear reconstruction methods. And this, as you'll see, is relevant when you have data at many orients. There's a whole bunch of other things the code can do. That's what we set out to do. But along the way, there's a bunch of sort of ancillary things that I think many people might find useful. Predominantly simulating images. Once you've built that geometric transformation function, you can then use it to, say, predict a priori what a GRISM scene might look like. Or you can use it to determine in a given GRISM image, which pixels belong with which source at which spectral or order, and so on and so forth. So you can do a whole lot of other things once you have those tables. So now I want to talk quickly about the order of operations that one has to go through to do this analysis. So it's really important. Do you remember the first step is the WCS transformation? So this is kind of a problem for HST. So some of you may be aware that all images from HST, the direct images, F775, F814, and so on and so forth, all of those images get tied to Gaia. However, the GRISM images, which were taken either as pre or post imaging, certainly as companions, they don't get tied to Gaia. Therefore, what happens is the sort of astrometry of the imaging sort of gets more advanced than the astrometry of the spectroscopy. And so the whole point of the pre-imaging was to tell you, as the user, where your spectroscopic image was pointed on the sky. Therefore, this choice to upgrade the imaging but not upgrade the astrometry is one that's actually quite critical for us. And so I'm calling that syncing the WCS, because we need to bring it back in concert with the direct image. Now, we have a number of tools inside of Slitless Utils. I'll talk about you can upgrade the WCS, you can downgrade the WCS, you can input your own WCS, or probably what's most useful is you can just simply sync them. So if you've got a direct image, like say a pre-image and a spectroscopic image, you can give it both of those and it will find the transformation that it needs to apply to the GRISM image to bring it to match the direct image. And that's just done via an affine transformation. So it effectively just wants to find the linear transform to go between any two WCSs described in your direct image and then apply it to the GRISM image. And that'll make more sense when I go through the example. But it's worth noting the amplitude of that tweak. So typically for, say, ACS, the matrix is very close to diagonal, so you can see it's almost an identity matrix, but it's not quite. This is more a reflection of, we can actually determine the rotation of HST blindly fairly well. However, the pointing can be off quite a bit. So you can see it can be off by typically even as much as 0.1 arc seconds. And so, as I'll talk about in the notebooks, a shift here will either manifest as either a redshift error in your output spectra, or as a flux loss, because you've simply moved the aperture off of the spectral trace. And that really depends on to which axis you have made that error. For the optical data, you need to do cosmic ray flux or cosmic ray masking. There's a whole bunch of common techniques that people have used. I've sort of embedded all of those inside of Slitless Utils. This is an example where you use the Laplace kernel masking. So you look for, or you recognize that cosmic rays are sharper than the point spread function. And so you sort of filter the image based on the second derivative of the image, where you're looking for things that have really sharp, discontinuous profiles. And so this is an example where I used a simple, convolution kernel to do second derivative computations, and you can see, well, I don't know why it's not animating. There it goes. There you can see the things that it's masked as cosmic rays. I'll note that there's other techniques. For example, if you have repeated measurements of the dithered field, you can use those to mask for cosmic rays, and all of that's built to Slitless Utils 2, if you would prefer to use that technique. You need to do sky subtraction. This is a really confounding step that I think gets lost and sort of underappreciated. I think this is really critical when you're trying to go faint, and this is what most people are after, right? So this is done by looking at repeated observations of the night sky and comparing them to your data. So the way it works is you've got here on the lower left some science image. This is again ACS. And we've built up through diligent observations of the sky over the years this model. And so the name of the game is find a scale factor that I can multiply this scaled image by and then subtract it from the scaled version from the smoothed image and result in this residual map, which I'm calling it residual, but you really should be thinking of it as background subtracted. That was for ACS. WIFC3 looks like this. These are the WIFC3 IR backgrounds. You can see a lot more structure in here. I could give an entire description about all the structure that you're seeing here, but I won't go through all of that. I will caution you, however, because of the nature of HST, because of its orbit, because of the properties of WIFC3, there's a standalone technique here called WIFC3 backsub. So if you're looking at WIFC3 IR data, please consider that code instead. It's actually better. I won't get into reasons why, unless you really want to know, I can explain it. But that's the same algorithm, but working on a finer time scale than what Slitless Utils is working on. So I'm just going to flash this up and immediately move past it, but I wanted to, again, we're all here usually for the spectral extraction, and like I mentioned, we have two forking branches on this, two different techniques. This will make more sense once I go through the actual notebooks. And of course, we have some additional modules to do additional things, such as grouping, region, simulation, and tabulation. I'll leave this up here, and you can just peruse it for a moment. I'm going to go through all of these things here in just a second in the notebook, so it will make sense what all this stuff is. I want to do one more slide before jumping to Jupyter to do some examples. If you've worked with HST slitless spectroscopy in the past, you have probably been sort of confounded by needing to obtain the reference files. Historically, the reference files for WIFC3 and ACS have been distributed on those instrument teams' web pages. And this leads to sort of this complicated version control. How do you know that you're using the latest reference file? How do I know when trying to debug your problem as an instrument scientist that you have the latest reference file, maybe you have the old reference file? How do we keep track of this kind of stuff? For JWST, this is really transparent. For HST, it's not so. So we are pushing a new way of handling the reference files for HST. So what I have done is I have captured all of the current best versions of everything, staged them on a box directory, and Slitless Utils has the functionality to go and fetch the latest reference files for whatever instrument or for whatever setup you have. So if you've ever used like CRDS get best refs, this is effectively emulating the same behavior. It's just inside of Slitless Utils. This is definitely a place where we want a lot of feedback on. If you've encountered these problems that I've alluded to, if you go and use Slitless Utils reference file manager, let me know what you think of it, because this is work that's being seriously considered. I will say that once Slitless Utils pulls them down, they're going to end up in your home directory in a directory called .slitlessutils and then the version number of whichever reference file data set you're working with. So I think we're currently on 1.0.8, but it will chunk everything in there and it will grab them all locally. So now I want to go do some code demonstrations unless there's some questions here. Right. OK. So here's Jupyter. Everything's written in Python. Hopefully, everything that's written here is stuff that should now be obvious. We've got a read the docs page you can check out. The code is all, of course, open source on GitHub. So there you can go and clone the latest thing, fork it, and make modifications yourself. Again, the installation. Oh, I should say, this is the notebook that's on the Slack. So if you want to go and grab this on Slack, you can work along with us here. As I mentioned, all of these tutorials I'm going to go through here, this is all just cut and pasted from the slitlessutils.example subrepo. So I'm a big fan of this because that means that we can integrate all of the examples inside of the CIDC testing and make sure that the examples always stay up to date and in sync as the code evolves. It also means that you can just go and look at the source code yourself. Once you've pip installed or cloned or whatever, you can go and see these codes yourself and see how you gesticulate. How you might want to modify the workflow to your benefit. So the first tutorial I'm going to go through is how you would analyze some ACS wide field channel data. This is going to be the exact analysis that we go through to analyze the calibration star, the Wolf Rayet 96 standard star target. So this is a little flow chart that shows you what we're going to walk through. Each of the two yellow boxes, this is some pre-processing step that may or may not be relevant to you and your particular use case. For example, let's suppose you want to look at all of the FIGS data of the ultra deep field. Well, you probably don't need to pre-process all of the direct images associated with the UDF, right? That's an extreme undertaking. Anton and others have already done that for you, so you probably don't need to do this lower bottom yellow box. But in this sort of standalone thing, we need to build that direct image ourselves. So of course, there's the obligatory imports. Just going to set some global variables for what data we're going to be looking at. I think most of this should be obvious. I will call out 2 points here, the filter and the 0 point. That's the name of the direct image filter and the 0 point associated with it. I realize that a lot of the 0 points evolve with time, but the 0 point is not really used for very much. It's really only used when you're doing a simulation, right? So you would want your simulation, I think, if you have a direct image and you know this star, this high redshift galaxy, this whatever is a fixed magnitude, you would then want that magnitude to then appear in the sort of spectroscopic image, where the spectrum is normalized to that magnitude, such that the spectroscopy gives a consistent result to the photometry. And so that's really all this is used for. So even if you change this number by even a large amount, it will do nothing. It will just keep the imaging and the photometry, the photometry and the spectroscopy in sync. These data, we have, they're one-to-one, meaning that every prism or every spectroscopic image has a companion direct image. That's not always true, especially in later years where we found that you can do, say, a single pre-image with 3 or 4 spectroscopic images, in which case you just have to modify this sort of workflow just a tiny bit, but this is how these data were collected. And this is the position of the source that we're going to be analyzing. So, do you have a question?
Yes, and we allow questions.
Yeah, please.
Okay. So you said that
I'll run this. It's slow.
It was starting with Gaia, but you did not like that because there was a difference between the Gaia, WCS, and then the spectroscopy. So what happens if you have pointing errors in the direct image and you're no longer trying to Gaia? You do like.
What matters is all of this is going to be driven by the segmentation map. And so, I can erase the WCS from the segmentation map. What I need the astrometry in the spectroscopy images to match that of the segmentation map. And the issue with Gaia was that I'm deriving the segmentation map from the pre-images. And so since MAST has shifted the astrometry of the pre-images, there's no longer this connection. That has been broken. And so I need to enforce it. And that's what one of these steps will be.
Okay, but you're giving it an RNA tag.
Yeah, that's right. It's completely nonsense.
Oh.
It's somewhat circular, right? I ran the notebook, found where the star was, and then I put that number in here.
Yes.
Yep, good call. First step, I'd fetch the data. So if you're not familiar how you can use Astro Query to fetch HST data, here is some code. Dissect it. The data were already here, so I'm just going to use the cache versions. Now we're going to have to pre-process the slitless images. Generally, this is the workflow that I recommend. We need to update the WCS, and then we need to mask the cosmic rays. We can mask the cosmic rays either with a Laplace kernel, like I mentioned, or you can do, say, a bit like Drizzle does, if you're familiar with Drizzle, to mask bad pixels or cosmic rays. So we can also do that. And so now you can see why, well, if we want that to work, then we also need to match the WCS. So that's why we put that second. Of course, once you've masked the cosmic rays and then you want to go do the background fitting, well, I guess it makes sense to do the background fitting last, because now you've got the sources in the right spot, or at least the right relative spot, and you've masked the cosmic rays. So that's going to help the background masking. And so you can see this little script is basically just doing that. I'm going to downgrade the GRISM files only here because I'm going to show you how to upgrade them later. So this is basically, I'm going to take the direct images, or the GRISM images, I'm going to bring everything down to the same level, basically undoing the Gaia updates. And that's going to run, you can see here it's running Astro Drizzle, and that's because what it's doing is it's Astro Drizzling together all of the spectroscopic images to mask the cosmic rays that way. Okay. So then we also have to do the same thing to the direct images. Again, this is the step most people probably won't have to do. Like, for example, if you were looking at the FIGS data of the UDF, you wouldn't need to do this step, because this is where I'm going to create the segmentation map. I'm going to create the mosaic that you would just go and fetch from the UDF, or you would fetch from candles, or you would fetch from whatever survey you're tying to. But we don't have that here for this. I will say there is one step, there's one gotcha, that even if you are using some images that you've gotten from some other mechanism, you still need to populate some things in the header of the segmentation map. And that's these three things here. That's just so slitless utils can know, again, back to the issue with normalizing the spectra, so it knows which filter this goes with, what is the 0 point that goes with this. That's all. Again, this is really gentle information that really has no significant bearing on the outputs. So did it run? It's running. Yeah, that's slow because it's calling astrodrizzle. So I'll go on while that runs to, again, reiterate some of the things that I said about the WCS, because this is, in all my years of working with these data, this is always the problem that bites most introductory and novice users, is the WCS. So what we require is the segmentation map or a catalog or something that tells you where the sources are in the sky. And then we need the GRISM or PRISM images to have the WCS that's consistent with that catalog or with that segmentation map. All of that stuff can be off and shifted off, way off the sky, but they do need to be consistent with each other. Okay, and so if you don't have it consistent, so if you have an error in the dispersion direction in your astrometry, well, that's going to translate directly to a velocity or a redshift error in your output. If it's perpendicular to the dispersion, then it's going to immediately introduce as a flux error because you've just put the aperture off. So I broke it down into sort of a two-question philosophy for you. If you have an existing mosaic or segmentation map, then you need to, you've probably made that mosaic by doing like tweak reg on your direct images. Well, then you need to find whatever perturbations were applied to your direct images and apply them to your slitless images. And there's utilities in here to do that. There's affine updates and so on. If you're going to create one from scratch, say from your pre-imaging, well, then you need to just fight this issue in MAST where the pre-images are put on a different rastrometric reference than the spectroscopic ones. Fortunately, everything is recorded, so you can easily do this. And so these are the two function calls to either downgrade your WCS or upgrade your WCS. And I'll show you what that looks like here. So there's this little handy-dandy function called list WCS where you pass it a glob input. And what it will show you is, say, in this particular FITS file, JXQFLC, well, there's two detectors. It's ACS after all. And in each detector, there are 4 WCSs present. And it will tell you the provenance of each one of those WCSs. And so you can see Opus. If you don't know, Opus is sort of the generic, the most basic one that the pipeline inputs to the files. And then successive iterations based on some running of tweak reg. This is putting in, say, the GuideStar catalog and the distortion model and so on and so forth. And so what's critical here is that the WCS that's being used, which is the boldface one, which is the one that doesn't have the suffix name on it, or the suffix to WCS name, it's critical that this match between all of the images that are going in. Right, and so I've asked it to give me the WCS for everything, regardless of spectroscopic or imaging. And here you can see what I was talking about. The direct images have been tied to Gaia DR3, whereas the spectroscopic ones have not. And so if you just used this WCS, thinking, oh, well, Gaia is more better, I should use the better one. Yes, of course, but then it won't match this, and therefore the sources will all be shifted. So what we're going to do is we're going to take these images, and we're going to roll back so that they have the same WCS. Cool. And then extract the spectrum. That's what we're all here for. This is, I'll say, doing the canonical spectral extraction using like Horn. It's what's the algorithm that's in AXI, for example. And what good would it be to not look at them? So this is, the blue is what we've just measured. The orange is the wavelength calibration spectrum from Anna Pasquale, just smoothed to the spectral resolution of the grading, of this grading. And you can see, okay, maybe there's some slight errors in the wavelength calibration, but maybe nothing too problematic. So that's how to walk through an example for ACS. WIFC3 would be exactly the same, except for things like the cosmic rays are a little bit easier to work with in WIFC3 IR. Okay. All right. So the next really cool thing that's inside of Solidus Utils is that it can do simulations. So this is, depending on your thought in the world, either absolutely critical or a complete waste of time. So I'll just go through it at a high level. Here's the same sort of flow chart where we have to now decide on the assumed properties of the spectroscopy that we're going to simulate. And then we have to make a scene. Now, maybe you don't need to make a scene. Again, maybe you've got, say, I don't know, the goods data, and you want to imagine what a G800L would look like on this goods field, in which case you don't need to do the yellow box. That has been provided to you from Jivalisco or somebody. I'm going to go through the yellow box anyway, just very, very fast, so that you can see how one would do that if one wanted to do that. Again, the code imports. Again, setting up the same kinds of things. So this is nominally what we think the pointing of the mosaic will be. Some properties, I think, that are probably obvious of the mosaic that we're going to create. We're going to imagine that we're doing 3 GRISM observations. We're going to name them A, B, and C. The telescope, and so on. The blocking filter, this is for JWST. We'll come back to that at the very end. And then a few other things that are not very important, except for down here, the spectroscopic catalog. We're going to use the Pickle Stellar library. Doesn't really matter. You can use any old library you like. We're going to imagine that in these 3 images, there's going to be 3 sources, object 1, object 2, object 3. You can think of this as what's going to be in the segmentation map. These are the positions of the sources in the segmentation map. We could have done it as RA and DEC, doesn't make a difference. This is the magnitude I want them to be. So again, the image will have them, they will have this magnitude in the image and this magnitude if you convolve the spectrum to be there. And these are just the SCDs that we're using. Just using the Pickles library because it's in CRDS and I can fetch it programmatically. So this snippet of code, I'm not going to go through it, is basically just making a 2D image that you might have gotten from AstroDrizzle of a direct scene where we've got 3 point sources in there and create a segmentation map along the way. Again, this is something you probably will download from the UDF or from goods or from candles or from something. But here's where we actually get to the spectroscopy part. What we need to do is we need to make a CSV file that tells us the properties of the observation. So we need to tell it, the file we want it to simulate, the name, where we want that GRISM field to be centered, the orientation we want of that GRISM field, and then a bunch of things about which telescope we're using. Right now we're only considering HST, but we are working on JWST and the blocking filter as well. The exposure time, you can add a 9th column here to include the exposure time if you like. I think it's hard-coded as 1,000 seconds if you don't pass it a number. So we're just going to write that out as a CSV file. That should look fairly easy. And then we want to do the simulation. So when we come to this part, this is one thing I want to stop and mention here. We have to load the GRISM images. So we have these things called collections. So there's a WFSS collection that's just going to be all of the GRISM files sort of encoded. Since we're loading these from a WCS file, we're imagining these as being something we want to determine. So this is just a lightweight container that contains that stuff about RA and DEC and roll angle and so on and so forth. And it's really just lookup tables to that kind of stuff. And then we have to pass it something about the segmentation maps. So you can see that we're passing them as _segs and so on and so forth. And then we're going to write the spectra that we want as inputs to disk as well. We run the forward model engine that I mentioned in the beginning with that rainbow simulation, and then run the simulator. And so now we'll just look at the images that we've created because we did the work, why not? And so this is now just the first order spectral trace of the 3 fields that we just created in the 3 different roll angles. The top row is the science image. The second row is the uncertainty map. It's just got the Poisson statistics in there. There are, depending on the camera and instrument you use, things like the dark current, the read noise, that kind of stuff is encoded. errors like flat field errors are not represented here. So I wouldn't get too hung up on like if you measure the signal to noise from these things, if it doesn't match to the 10th decimal place to the ETC, don't get too worried. These are really meant more of like to give you a sense of, what position angle do I need to get a clean roll angle of my particular target. And that's really how I use these kinds of things.
Is there any PSF information that you can pull here if you're still deciding?
No, that's something we're working on. So the PSF, that's a good question. So the PSF is taken from the direct image. But the wavelength dependent PSF, the problem is that's very poorly known from HST. So it's not being folded in, but Massimo will talk on Thursday about how to integrate that into these kinds of ideas for Roman and for Web, where we do have that information. Okay, so any questions on how to simulate? I know it's really fast, but. So we could just go through now that same thing that we just did to say extract the sources that we just did. Easy peasy, it should be obvious what's going on at this point. We're loading the sources and we're doing something with them. In this case, we're going to make DS9 regions. I'm not going to look at it. I think you all can imagine what that's going to look like. You're going to open up a DS9 image and there will be a region drawn around the first order spectral trace of the source that we've identified. So this is something I use to know is the astrometry right? I can look, if the box lines up on the object, it's right. If the box moves off to the side, something has gone catastrophically wrong. Or maybe if I want to know, hey, I see this spectral trace, which object did it come from? You can use it to this same end. Again, we've got simple extraction, which is more or less the same algorithm that's in, say, AXI, is in Grizzly, is in Horn. These are the canonical 1D extraction algorithms. And now I want to take just a few minutes to sidestep back to a little more pedagogy to talk about the linear subtraction or the linear reconstruction techniques. So we're all here because we understand the power of the slow spectroscopy, but how we deal with the contamination is the real problem. So I'm imagining here in the lower left corner, I have 2 point sources, a red source and a blue source. These are not saying the objects are red or blue. We just want to guide your eye through the process. And as any good detector works, it disperses to the right. So this is what we would get, say, if we observed these 2 things in some spectroscopic image. But if we imagine rotating the telescope and redispersing, well, now the 2 sources pull apart. And that's sort of what you saw in my notebook before. And so we have looked for ways where we can simultaneously use the information. Sort of pedagogically, we have 2 unknowns, spectrum from red, spectrum from blue, and we have 2 observations, horribly contaminated, nice and clean. So this is a solvable problem. 2 unknowns, 2 measurements, let's solve the problem. So to deconstruct the problem, looking back at that source, each one of those things, because those stars have a different detector position, they therefore have a different wavelength scale. So that's the key to pulling this thing apart. So if we zoomed in on this pixel, well, that pixel is going to be some weighted sum of the blue bit plus the red bit. And I just decomposed that over here. So that's, say, the blue spectrum at 1.1 microns times some weight, plus the red spectrum at 1.3 microns times some other weight. And those weights we can obtain from that forward model. That's that forward model. And so that leads us to this big linear equation. Well, all we have to do is recognize that the flux in any given spectroscopic pixel is a weighted combination over all of the sources, over all of the wavelengths, and we just write down that linear combination, and now we're going to solve it. So the goal is to solve this system using sort of least squares techniques, but the problem is that it's an over-constrained integral problem, and this linear operator, W, is ill-conditioned. So ill-conditioned is a fancy way of saying that small changes on the input lead to big changes on the output. So we need to control that problem. That problem is controlled by other means. If you're familiar with AXI and Grizzly, that regularization is controlled by, say, folding in that it needs to match a polynomial model, or it needs to match the photometry. That constraint is the same thing that we now have to introduce in a more data-driven perspective. That's done with taking off regularization. So you can think of this mess equation as this first bit. This is just the chi-square that we all know and love from grad school. The second bit is the regularization to help us keep control over the condition of the number of the matrix. And this little scripty L, this is just a regularization parameter that we need to trade between regularization, meaning smooth outputs, versus modeling the data chi-square. You can think of this again as the degree how reliant you want to be on the polynomial model or the SED model or the broadband photometry in doing your decontamination study. So I want to say there's just a couple of quick points. Regularization is a standard technique used all throughout the mathematical literature, but I'm going to talk about it, and a lot of people do talk about it in terms of damping, as it damps high frequency oscillations in the output results. And so that's just going to look a bit like this. I'm not going to spend any more time on this slide, but you can show here on the upper right that when you do the damping, it's going to tend to lead to smooth solutions around whatever input initial condition you give it. I will say it's probably worth thinking about that equation for a moment. If you took L to infinity, then the second term dominates, and in which case the minimum of that will happen when F goes to 0. Whereas if you let L go to 0, that will go back to the pure maximum likelihood fitting, then you're only sort of putting weight on this first term, and in which case every single noise peak in the data will contribute information. And so L really is just a trade-off between those two extremes. So how does it work in practice? This is an image which is very similar to the one that Zhen showed before lunch, or just after lunch. This is from the FIG survey, something that Sangeeta led, that Nora and I did a lot of the work for. Where you're imagining we have some direct image of some galaxy here, and we've observed that galaxy at 5 angles coming off sort of radially. And you can see that if you disperse along, say, the major axis of the galaxy, it may be angle 262, then you get a very broad spectrum. That's, again, because the line spread function is coming from the size of the object projected along the dispersion direction. Whereas if you observe along angle 196, something more along the minor axis, you can actually resolve the two spectral features here. And so this shouldn't come as a surprise. And so this is what leads a lot of people to say, well, when we do this, we have to make a trade-off. Do I only want to look at data at angle 156 and angle 196 because of the highest spectral resolution? Or is there a way I can combine them to get the total signal to noise of all 5 orients, but retaining the spectral information of the 2 really sharp orients? And so that's what we found this technique does. And so this is a comparison of a given object to extractions from AXI, that object we just looked at, and now you can easily see that that line is H alpha and sulfur 2. And so what you do is you actually improve the spectral resolution to the orient of the highest in the data while retaining the signal to noise consistent with the full data set. That was a comparison to AXI. Here's a comparison to the 3D HST from a different source. And you can see things like the O3 complex becomes easily disentangled, separate from the H beta, and so on. The last thing I want to talk about is source grouping. Because of the way that the linear reconstruction techniques work, you have to link all of the observations in one pass. So you might want to find ways of paring down that problem. If you've got a lot of sources, you can have lots of contamination. So what I want to give you is a Gedanken experiment here, where imagine I have this idealized field of these 7 little ellipsoids here. And imagine I observed them in a single orient that dispersed off to the right. Well, then clearly objects, say 1 and 5, are going to overlap in the dispersed image. Objects 2, 4, and 6 are going to overlap. And that's what I'm trying to show here in a graph theory sort of way, that objects 2, 4, and 6 get linked together, objects 1 and 5 get linked together, and object 3 is all by itself. And if this were all the data you had, you could have no problem analyzing object 3, object 7, no problem. You'd be in trouble with how you deal with objects 1 and 5. You'd have to introduce more information. You might imagine this is what I'm going to say. You rotate the telescope, and now you've got a different orient. And now you can see a different sort of collection of contamination patterns. But what we're really thinking about for this is the aggregate, all of the contamination dealt with in one go. So now you can see that objects 1, 2, 4, 5, 6, and 7 if we wanted to treat them in this multi-orient framework, they have to be linked together in the analysis. Whereas object number 3, it never overlaps with any other source in this fictitious survey. Therefore, object number 3 can be dealt with separately. This is sort of pedagogically the same as taking that linear operator and block diagonalizing it. And so, slow spectroscopy is moving really much into the realm of resolved spectroscopy, so I want to say a few things about that too. Here is a segmentation map that I've made from, I don't know, one of the Clash clusters. I don't remember which one. But you can see the colors represent the pixels associated with different galaxies as part of this cluster. And canonically, as I've been framing the problem, what we're imagining is we're extracting each one of these colors as a separate source. But one doesn't need to do that. You could just tell slitless utils every single pixel is a separate color, give it its own separate segmentation map. And then it's going to go through and find the 1D spectrum that best reproduces the entire data set, thereby deriving another IFU representation. Now I want to stress, this is completely data-driven, right? No SED models are used here. I don't need to assume that the galaxy is at this redshift or has this velocity field. That's the determination. That's what we're looking for. We don't need have any priors on any part of the problem. It's a pure data problem. The downside is it requires many dithers, many orients, lots of data have to go into this. This is maybe not so powerful for HST because of the limited data volumes, but this is a place where Roman is really going to shine. And so I want to invite you to come back and hear my talk tomorrow morning on Roman, and then again Massimo Griccio's talk on Thursday, where we're going to go into this technique into a far bigger detail. Yeah, please. No, take a long time. Sorry?
What does Betty mean?
Betty? Many. Oh, many. Yeah, sorry. I thought you said Betty. I'm like, who's Betty and what is she doing here? Yeah.
What number is it?
Yeah.
Is it 3? Is it 300?
Yeah.
That's quite a lot of difference.
Exactly. So I can tell you in passing that my stupid animations, me and my pedagogy. This data set here has 5 orients, right? And so you can see what it does for the spectrum here, right? So this is a real demonstration what 5 gets you. And this would be, say, if we're treating the whole galaxy as a single unit. If you want to decompose it into little subcells and get like an IFU-like data product out, well, then you need to be conscientious of, inputs versus outputs, number of free parameters versus number of unknowns, and that kind of thing. One of the things that I have mused on is when you think back to this linear framing of the problem, this matrix W, I've told you that it's ill-conditioned. You could ask me what the condition numbers are on it. And so I think the condition number is telling you something about that. So typically for a problem like this, the condition numbers are about 10. If you wanted to look at some of the Roman data that Massimo will be showing later this week, they have condition numbers more like unity. So we think that means something like between 5 orients is good for a big galaxy. You need something like tens of orients if you want to decompose it in an IFU-like basis. But this is hand wavy because it's coming down to inputs or number of unknowns matching number of knowns and so on. So I'll stop here. I have some more demonstrations in the notebook that will just go through how to do the linear reconstruction techniques. But I think at this point, you all know enough that you can click Shift-Enter as well as I can and look at the plots that it produces and see how to reconstruct it yourself. So I'll stop there and take any more questions. I'll leave you this. So you have ways of giving us feedback. So the code is all available on GitHub. You can clone it, fork it, delete it, I don't care. Then there's also, you can put in stars tickets. So I don't know if you all are familiar with that, but you can put in a stars ticket that will then trickle through the system and eventually land on my desk or someone like me's desk to answer your particular problem. So depending on what you want to do, if you want a concrete code change, go to GitHub. If you have a gee whiz, I don't understand how this works or why doesn't this work, submit it to me via stars. Thanks.
Hi. This is awesome. I think it's super cool to have all these tools in sort of one place, and the idea is clearly it looks like you're going to think about James Webb and Merlin eventually. I'm just curious because I know there's a lot of people in this room who have, like me, used Grizzly for all their helpful work, and you pointed out some differences here and there, but say I was starting my PhD today and I'm like, what's the best pipeline to use to produce my HST data? Can you sort of summarize what are the advantages of slit utils over something like Grizzly that is now?
So I won't try to summarize the components to Grizzly because I think there's people here that can do that better, right? But I will say that this has really two advantages, in my opinion. We have the linear reconstruction framework, which depending on your data set can be very powerful. So if it wasn't clear, let me just put a finer point on the linear part. We think about contamination, two objects overlap in the dispersed plane. We think object 1 contaminates object 2. Well, in the linear framework, in the linear philosophy, there is no thing as contamination. Contamination doesn't exist, right? But rather, these two objects overlap, and all we've measured is the sum of two things. The measurement is fundamentally a degenerate thing. We've measured object 1 plus object 2. And so we're treating that problem from a mathematical first principles way. Insofar as there is contamination, I would describe that as sort of the boundary effect, right? That in your given dispersed image, like though I show this as a cartoon here, this isn't the end of the story, right? There are galaxies, there are stars off the field, and they might well disperse light onto the detector. So that unknown known, right? We know there's things there, but we don't know anything about them. That is now the contamination problem. We've moved it to that as being the issue. I think the second sort of advantage here is this is a completely sort of agnostic framework to what you're looking at. Like in my day job, I study low mass stars, right? And so low mass stars don't really fit well into the scheme of redshifts and line identifications. And we've seen a lot of the spectroscopy focusing on high redshift galaxies, and that's all really interesting stuff, but that doesn't really map onto brown dwarfs, for example, right? And so this is a toolkit that is agnostic to any type of pre-assumption on what kinds of questions you're going to ask the data. So this is going to give you the purest spectroscopic measurement. Think of it more like the difference between, say, using source extractor versus using bagpipes.
Can I ask a follow-up?
Please.
Sorry, because I'm very interested in resolve stuff. So you mentioned it briefly. I'm just curious where that is and what the plans are.
Yeah, so at present, it's simply just this. It's you give it a segmentation map. It doesn't care what the segmentation pixels represent. In this case, I'm treating like this whole thing, this whole purple thing, as one source, meaning that everything in this image, everything that's purple, has the same spectral shape, just scaled up or down based on whether or not it's in the core or the wings of this elliptical galaxy. Instead, if you gave it a segmentation map, oh, wrong keyboard, where you've now put a different segmentation value in every pixel, it's going to give you the spectrum at every pixel. So I don't know, there's maybe 2,000 different colored dots here. So it's going to give you 2,000 spectra, which you can then stitch back into an IFU cube. And that's the way slitless utils does it. I think you can, with some trickery, I think if you go in and you relabel the segmentation value as negative, like -2, it will do this trick for you. And it will output the IFU cube for you. I'm not 100% confident that's what we were working on, so I think it will work, but just in case this does work. But I will say that later this week, Massimo will talk at length about how to do that rigorously. What's up, Nen?
Can you give us an idea of the computational size of these linear reconstructions?
What was the word? Near?
These linear reconstructions.
Yeah.
Either you have 100 sources and they're all overlapping in a real data set, or you're doing this.
Yeah. So.
1,000 different.
Yeah. I think I get your question. So far and away, the hardest part is building the linear operator. Mm-hmm. Once you have built it, it's really fast to use. Massimo will show examples on Thursday where, depending on the size of the problem, it can be between sort of an hour-ish to many hours-ish. We found lots of ways of speeding up this technique since we first derived it a couple of years ago.
Yeah, I guess I was asking like about the size, like.
Oh, the size in like gigabytes in memory, you mean?
Yeah, or more like from a heuristic standpoint, like, so you have, I'm just trying to think through, like, you have 2,000 pixels in your direct image. You want those all to be spectra, which make up X number of pixels, and then each one overlaps with how many others.
That's right. So this is a 2D array of numbers.
Yeah.
One of the dimensions maps between outputs, and one of the dimensions maps to inputs.
Right.
So the outputs are really easy. You've got 1,000 sources in your catalog, and each source has 100 spectral elements. Ergo, you have 100,000 elements in one axis of that matrix. The other matrix dimension is the number of inputs. Well, that's every pixel you have. So suppose you were looking at WIFC3IR, that's 1K by 1K, or there's a million measurements there. And maybe you've got 100 images, so therefore you have 100 million numbers in that other row.
Okay.
Now, by construction, the matrix, we never actually render a matrix that's 100 million by 100,000. That's not tenable. But it is an incredibly sparse system. For the systems I've been showing you, the density is something like 10 to the minus 5%. So we treat it all as sparse matrices inside of the code, and sparse matrices are doing all the work.
Okay, thanks.
Is that what you're getting at?
Yeah, a lot closer. We can talk later.
Yeah, such that the final output is, the matrix is only like 5 gigabytes in memory.
Okay.
Yeah, it's very elegant. So a few questions. The first is that, so again, you are using linear combinations of spectrum to add them. But how do you do the gas of each of the spectrum, the first one, and also for the objective function you are using the first term is just, if I am right, is you're comparing the image, the constructed image, reconstructed image with the observed or simulated image by pixel by pixel. Have you thought about maybe adding other terms? Maybe, let's say, if you are, except the two sources are exactly the same and that same row, the y-axis will be different because it's
that's right.
Mixture of two PSF links.
Yep, that's right. So right now we don't fold in the PSF, and that's purely a limitation of HST itself. JWST and Roman have significant utilities on board that we can determine the wavelength dependent point spread function sort of in semi-real time, where that's not really possible by HST. If you've ever used like the Tiny 10 PSFs, or if anyone's familiar with the Tiny 10 PSFs and those problems, that's the same thing that I'm saying. So therefore we don't expressly fold in the PSF other than take it from the direct image. So if you have a G8 or a F775 image that's got a PSF baked into it, we are tacitly assuming that that PSF in 775 is the same as the wavelength dependent PSF in, say, G800L. That it's the same, that it's, I guess, gray, not depending on wavelength.
Okay.
And so that then gets folded through. But if you wanted a true multi-wavelength thing, like what Andrea was asking, that's something that's got to come from Webb and Roman. Again, if you've used like Webb PSF or STPSF, we don't have such a thing for Hubble, and that's the limitation there. The objective function, this regularization is to just damp out discontinuities. And so I think you asked, maybe if I'll reframe it, about what the initial condition is, and that's what this line of algebra is trying to show you. So suppose you had an initial guess for what you think the spectrum was.
Yeah.
Right? Maybe say the broadband photometry, for example. That initial guess is what I'm calling F tilde here. And so then you can plug F tilde in and then look for perturbations around the initial guess, and that's what I'm calling delta F. And so because it's just a linear process, it probably doesn't surprise you that what comes out the back end is a different linear equation that has the same sort of mathematical structure, but now just the variables are renamed. And so what the code actually does is if you give it an initial guess, it will use that and then look for perturbations around that.
How do you know it's continuously perturbed, but not trapped in your local?
Let's talk about that offline. Yeah. Did you have a question? And I'll be done here.
Yeah, hey, this is really great. I had a comment actually, because I was trying to actually use this last week. And what I found is that I just wanted to kind of make an abstract field with big galaxies, and I couldn't figure out how to do it without an existing image. So thinking how you can just kind of completely simulate from.
Yeah, that's what I tried to go through really, really fast.
Okay. Without like an existing WCS and without an existing.
Yeah, yeah. So that's here in the notebook, which is now on the thing, or now on Slack. And so, for example, as you said, an existing WCS, I'll show you, so that you know I have nothing up my sleeve. Here's the position of the source. Oh no, wrong one. Right. Here's the nominal position of the mosaic that I think you were, which is what I understood you were asking about. The pixel scale of that nominal mosaic, the dimensions, 1K by 1K.
My pixels.
Yeah, that's right. And so it then makes a WCS that matches this. Yep. And so it will make a WCS that has this size, this pixel scale. I guess I didn't code up an orient, but yeah, I mean, I could have. And so then it creates a WCS here.
Yeah, so the other question was like, have you done any tests on how this scales to like run, for example, the wide area?
I will, but I'm going to let Massimo answer that on Thursday.
Okay.
Yeah. No, so I will talk tomorrow about the supernova pit pipeline, for which I'm the lead, and the linear framework is deeply embedded in everything the pit is doing. And we think we can do it, so, but I'll talk more about it tomorrow. All right, we're 5 minutes over. And I'm on Slack. We've got a Slack channel for this, so come ask your questions, bring your data.
Thank you so much. Russell, and you use your own computer, right?
Yeah.
Excellent. Yes, I think you will use your computer. Yeah.
Oh, she wants to use it.
Yes.
Okay.
Thank you. So, oh, sorry. Okay, so let's open the screen. Okay, wait, let me just put this on. I have no idea if it's on. I do not understand that sign language. Oh, okay, this is good. Oh wait, I'm doing the wrong thing.
You can quit.
Sure?
No, you don't need to do that. Just quit that.
Quit? Maybe. Okay, that's fine. Okay, hello everyone. I think we should also get the other discussionees. Do you want to come up? Yeah, so the three of us are charged with running the discussion session for today. And the main sort of comments, I'll just wait for the rest of our illustrious team to assemble. So we were charged with sort of assembling everything everyone has said today under sort of some main points set by our illustrious leaders, the SOC. So, I mean, the general comment for today or thought is current, upcoming, and future WFSS capabilities are poised to revolutionize our exploration of the universe, and we need to start thinking about certain things. So the first thing is, where will the major paradigm shifts occur? We have just put some ideas on the screen that came from our three brains. So we're starting with just thinking about asking the general audience first what they think the major paradigm shifts occur, and see where the discussion goes from there. However, if nobody wants to say anything, we can move it along. So does anyone want to start this sort of discussion of where they think the major paradigms will occur? And I don't know if someone needs to go around with a mic or something.
Maybe you can clarify what you mean by some of these data points.
So these are just our ideas. So for example, for the first comment, where will the major paradigm shifts occur? One of the talks today at the beginning talked about thinking about rare sources and how that's been
a big topic, at least with James Webb and HST. But now those rare objects are actually going to have sample statistics that they're no longer going to be necessarily rare populations or exciting populations. And so that's sort of a paradigm shift where what we thought is exciting and rare is going to change. And we're actually going to move towards getting demographics for these things. So that's just one point we could think of, and the other ones are there. But yeah, if you want to start discussing that, we can start talking about what people think about that, or... Nope. Okay, we can carry on through our points. Okay, the next thing we thought about in terms of major paradigm shifts is someone brought up the idea of things like when we measure the mass metallicity relation, we've always historically been sort of undersampled in certain parameter spaces. And that's obviously going to change now with things like Roman and Euclid. We're going to be able to sample those regions much better. So the high mass end, for example, with the mass metallicity relation, we're going to be able to determine that much better. And the other thing that hasn't been discussed today, which we would like to solicit from you guys, is the time domain science and how PRISM could revolutionize that as well. If anyone has anything to say on this.
I have a question.
Yes.
When we say we're going to solve mass metallicity,
well, not solve, but
I am not a metallicity person, but every single time people bring up those metallicity questions, there are 2 or 3 people in the room who complain about the specific ways of measuring metallicities. So what do you think, and what the other people who are the expert at this, are we going to know how to measure metallicity well enough to actually do this?
It's a good question. I'm not a metallicity expert.
Yeah, I mean, metallicity is really tricky. Like there are, even within the local universe, there's this the abundance discrepancy between the metal recombination line and the direct temperature measurement. And basically, even with James Webb, I don't think it's feasible to measure metal recombination line, metal ion recombination. That's because that tells you the metal abundance directly, regardless of the temperature, the electron density of the ISM. It just tells you because the metal recombination rate is just proportional to the abundance, but it's so weak. It's just not possible to measure outside our Milky Way, or definitely not like astronomical distances, like beyond redshift 0.1-ish. So that's the reason a lot of team calibrated this strong line calibration based on direct temperature measurement. Direct temperature 3363 and some O2 aurora lines, they are still strong enough to be detected in distant galaxies. That's I think a lot of work, for example, by Ryan Sanders and the Aurora survey. And a bunch of other teams, they have detected strong aurora lines to do electron temperature measurements so that we can calibrate the strong lines. But still, a lot of the measurements still assume typical fiducial, like KSB recombination conditions for the ISM. I think from recent paper by say the NGD team, is Noor in the audience? I think Noor published a pretty great paper seeing some deviation from the KSB recombination condition. They not just the NGD team. I think a lot of team found, Glass team included, found a lower Bellmer-Deckerman ratio than the KSB. That can be an indication of KSB violation, maybe higher temperature, and maybe electron density is different as well, so that the O3 can be significantly collisionally de-excite. The reason we see a lot of O3 H beta, low O3 H beta values, that does not necessarily indicate metapoor conditions. It could be like a really high electron density so that O3 is suppressed. So yeah, in my opinion, it's a really complicated problem. We need to perhaps maybe work with the theorists, like simulators, to develop like a bona fide comprehensive understanding of the ISM structure in the High-Z universe from first principle, and then compare their simulation with observation to understand better the physical conditions of the ISM. Yeah. So it's a complicated, but it's definitely worth pursuing.
It's a great answer, but it only covers half the problem. That's the gas metallicity. There's the stellar metallicity as well. No, I think
Anyone else have any thoughts on metallicity? Nope. Oh, is it someone? All right. Yeah.
I was just going to say.
From Farhan's work, I think I was struck by, you know, for the mass metallicity that we have at the local universe from like SDSS is tens of thousands of galaxies. And even 5 years into GWST, we're pushing it to a little higher redshifts. I mean, the sample sizes are still hundreds. We're trying to do the exact same calibrations. And so, I don't know. I wonder if there's some sort of sample. It's too small still, maybe, even with number of years of data.
So are you saying you think with larger samples it would help us, or are you saying
well,
I'm not sure if it will help us? Or
I'm not sure. That's the.
Yeah.
Thanks.
Okay, should we move on to the next point? So the other thing we were thinking of is the time domain part of these surveys. So obviously Roman is going to have a time domain component where we're going to get data in this kind of, how to say it, like multi-epoch data that we're not used to, at least the wealth of data we're going to get. And so it's something we haven't really had to think about that much, at least in galaxy evolution. And we were thinking if there's people who have thought about that and things that we need to think about in terms of how that will shift the field and maybe create paradigm shifts in these other areas of galaxy evolution or anything else.
Yeah, in particular in the Roman high-latitude time domain survey field, the prism observation will have many epochs. So we are not time domain person yet, but I believe we have many experts here. So
yeah, there's two people.
Anyone wanted to say something?
The room is mine, but yeah.
The Roman's going to have two time domain fields, a northern field and a southern field. The solid spectroscopy will only be in the southern field. The southern field will then be further hyperfine split between a wide and a deep. I don't remember the exact properties of the two, but I can say that the deep, which is the one that I'm going to be talking a lot about tomorrow, the deep has 72 roll angles. Each roll angle will have 8 dithers. Each dither will be 450 seconds. So it's going to reach an instantaneous depth that's quite impressive. But certainly by the time you stack through it for like you folks looking for high redshift galaxies and such, it's going to be extremely deep. There's of course the Sangeeta and James program doing something very similar, but that's on a different data set. And then there's also the deep field that's not necessarily time domain. It wasn't meant as time domain, but it's got many, many different sub epochs. I will say the time domain field is optimized for type 1a supernova cosmology. And so the time scales, the repeatability, that is driven exclusively by what we think, how we think supernova 1As will evolve at redshift 1 or thereabouts. And so the science team, we will produce time domains or spectroscopic light curves for all of the type 1As as we move through the survey. It's not going to be big data releases. I don't know what the exact time will be, but as we move through, all of those spectra will be available. Our pipeline that I'll talk about tomorrow, that is also publicly available, and then you can then take and unleash it on that data set or the GRISM data sets or so on. And so we think that a lot of the gains are going to be here in the transients and the high redshift supernovae and such. I'd love to talk to anyone who wants more about that. I mean, that's Lou, yeah.
Oh, no. Try to kill me. Yeah, you could. I could also add that I guess there's a program called RISE, which is supposed to do the same, make the same products for the core collapse supernovae that are generated in the time domain survey. But again, I think there's plenty of room for analysis tool sets. You know, how we deal with it, whether or not there will be just one or more than one pipeline for reducing those time domain spectra, et cetera.
Thank you. Yeah, I wanted to share a little bit from the larger time domain community side. We've recently started the Cross Survey Supernova Working Group, where we're basically planning for how like larger time domain collaborations can coordinate with planned Roman observations. I will say I'm actually going to give a talk on the third point, a lot of this tomorrow morning, but there are a lot of new opportunities for time domain science that are going to be opening up, especially with Roman, mainly expanding our coverage in time and redshift. And even though supernovae are very time dependent phenomena, and there has been a lot of work in recent years, especially on the early time data when we see these really rapid evolution. But there's a lot of stuff that we can do once these supernovae become less time sensitive. And I think there's a lot of opportunity for spectroscopic follow-up with wide field slitless spectroscopy, and especially on space telescopes that we cannot do from the ground. Right now, as time domain astronomers, are sort of the math we have to do is turnaround time for getting your observations versus what large aperture telescopes are available at the time. And when the clock is ticking, you often have to give up things like resolution or building up your signal in order to get that observation in a constricted amount of time. So this is one area that we see a lot of possibility of basically getting types of observations that we're often not able to do from the ground because we're under such a strong time crunch. And I'm really glad that Russell and Lou pointed out the 1As and the core collapse, because there's also stripped envelope supernovae and other types of supernovae that we've been talking about, and we'll be sharing more about that tomorrow during the morning session.
Any more thoughts on time domain? Or
So I mean, I also want to mention that changing look AGN are also quite interesting, and Roman could also uncover. I mean, so Ruben will look at the optical, and Roman would look at the infrared. And I think someone mentioned it today morning, if I'm right.
So the GWST and Roman can do a lot of time domain science for AGN variability, like especially for example, for the Roman high latitude time domain survey field, like it has a prism. You basically can have the AGN variability across the wavelengths in the infrared, and to starting like the different structures of the AGN, like you can measure the structure function at different wavelengths, for example. And of course, if like some high-res source may be very faint, you can still stack the spectra because the cadence of the high latitude time domain is very like good, right? The cadence is several days. You can, for example, stack like 1 month or 2 months data and to go fainter for those AGNs because you know the location and you can do the stacking and go fainter and the smaller black holes, for example. There are many things we can do, I guess.
Yeah, also don't forget lens stars. Because micro lens stars can be also a very peculiar phenomena to study and happen. The cross section is definitely higher in a cluster-centric field. Yeah, I hope it's covered by Roman like cycle 1 proposals.
Well, I just want to put a plug out. We now have all of these different transients that we'd like to take a look at. And it sounds like several people are thinking about it, but we have no unified transient alert monitor for all this. And that might be an interesting outcome of what we're thinking.
Okay. I think I'll just move on to the next point because otherwise it'll probably take ages to get through all of them. So the last point we thought in terms of paradigm shifts that we'll kind of discuss today was there were some talks discussing environment and comparing things like the morphology density relation. We heard a great talk on that in different environments.
And we heard some talks that talked about looking at protoclusters and AGN activity in protoclusters with slitless spectroscopy. Many talks talked about getting GRISM spectroscopy like sort of targeted over cluster fields. You spoke about that, and also then like looking at general fields. But you know, obviously with Roman and Euclid, that kind of distinction no longer necessarily needs to be there. I think this was there because we had these small fields of view, so we had to do these target observations, and we call that cluster and we call that field. But that's going to change because once you get slitless spectroscopy for a large area of the sky, you can now start thinking of environment as almost a continuous variable, right? Like you can start doing these things along the cosmic web. Those definitions may change, and so that could be sort of a way of thought that is changed, but also a paradigm shift in terms of how we look at things like the morphology density relation and so forth, and how we study it. And so we were curious whether anyone else has thoughts about this, maybe in their own work, and how they may think that we need to change the way we think about these subjects.
I actually think this is where maybe the biggest paradigm shift will occur. Well, this is just my biased opinion. Just because with Roman and Euclid, you have such a like an increased like field of view, right? Like a much larger contiguous coverage, as opposed to like, you know, even with the passage survey, it's like a lot of area in the sky, but it's like independent, like tiny little pointings in the sky. Not really great for a contiguous mapping of the cosmic web. What you need is galaxies with pretty accurate redshifts and over a large you know, field of view to fairly good completeness in order to trace the like, you know, true mass distribution in the universe, which I think we can finally get there now with Roman and Euclid's deep wide surveys. I think with like, you know, several square degrees, we can definitely get there, and we can, because there's like a conflicting amount of conflicting information from literature about like the dependence of, I think we saw this too, like, you know, dependence of morphology on environment, or dependence on star formation on environment, metallicity, things like that. I think if we can like properly map out with like high significance the cosmic web, you know, across large areas, that's when we can definitively answer some of these questions. And that's where, you know, like I'm personally very excited about Roman and Euclid data being used like that. Yeah.
Yeah, thanks. Sorry, I just wanted to quickly add to that is that I think the pure parallels have given us a bit of a teaser on that. So talking about cosmic variance, they try and beat down cosmic variance, but then with Roman and Euclid, we beat down the cosmic variance, but also get continuous coverage. So I think that's also an added bonus. I think Eva had a...
Yeah, I want to agree with the previous speaker that for me, this I think is going to be one of the big paradigm shifts. At the Euclid Consortium meeting a few months ago, somebody, I think from the cosmology team, showed reconstructions of the cosmic web, probabilistic reconstructions of the cosmic web based on the fault-metric redshifts from Euclid, and they looked insane. And so this is coming from the cosmology side. I would be really excited to see these merged with galaxy evolution, to see where we can really take it and stop thinking of the cosmic web as just a sequence of nodes, because I think there is a lot more. There's like the filaments and all of the in-between spaces that do, galaxies do experience different physical conditions. And I think this will be really interesting to look at with these large surveys.
Awesome, thank you. Yeah.
Yeah, I'm also really excited about this. And I was thinking a bit about what you were saying about kind of thinking of things as more continuous, but then I was thinking about, you know, how we try to link progenitor and descendant populations and galaxies that end up in clusters. I mean, clusters are actually discrete structures with these ICMs, and trying to like figure out where that evolution, you know, where that drives their evolution. And then we try to trace it back to the protocluster stage. So the protocluster stage has been like a huge problem, right? Because we take all of these overdensities at high redshift and we call them protoclusters, but do they actually turn into clusters?
Yeah.
Right? So if we're trying to actually trace this over time, we have to understand that. And some simulations have shown that the way that we can make that prediction, we just need much more area, right? You need to actually be able to map the protocluster over a huge area to actually figure out if it's going to turn into a cluster. So maybe we're getting a little bit closer to that, and then we can start to say, this is the progenitor population of this descendant population, and try to link that evolution in a more concrete way.
Yeah, I just wanted to ask actually on that, because my very noob sort of knowledge on this is that obviously when a protocluster evolves, it takes up a larger area on the sky at low redshift. And I'm just curious, has that been possible to sort of determine well with what we have so far, or is there a sort of major boundary where you think that, it's going to be fine now with Roman and Euclid because that's no longer a constraint, so we can answer X now in terms of the protocluster size? Or
So I think we cannot answer it now. We don't have the area. We don't have, getting enough area with uniform coverage with good redshifts to predict this down, I think is not currently possible. I haven't sat down and when in the Roman life cycle will we actually have enough to do this. I'm also very excited about SC surveys that might be coming up soon, maybe soon. I haven't kept up on the current status, but if we can pair these two things, that really helps a lot. But I lost what I was going to say with the protoclusters. So my favorite example of this is that, everybody takes a protocluster and they project it down and they say it's a coma cluster. Well, the coma cluster is a merger, so you wouldn't have been able to pick out the protocluster coma and then project it down. So we really need much, much larger areas to try and statistically say this guy is really going to collapse. It's that big of an overdensity that it's almost certainly going to do that follow that path.
Awesome. Yeah. Any more comments on environment before we move to the next major discussion point?
I guess the other thing that is missing is most of people are still talking about the galaxies now, but remember that galaxy only occupies a tiny fraction of the total baryon mass. So there are a lot of gas, right? So what we can do by combining those large scale, especially with Roman, for example, combined with 21 centimeter. If any people here has expertise,
that sounds cool.
Please feel free to,
Okay, I don't think anyone wants to talk about that from the looks of it. So I think I'm just looking at the time. Oh, is there someone here? Okay, good, perfect.
I talked with 21 centimeter people in our university Michigan, and I think it's for the deep tier of Roman highlighted by area survey is slightly challenging for 21 centimeter because the latitude might be too high, and a lot of those 21 centimeter has got to be actually in the south hemisphere. So they would actually prefer, if we want to do a cross correlation function, deep field in the south hemisphere probably with a negative DAC will be better.
Okay.
Yeah.
Okay. I'll quickly move on to the second topic, which is basically what can we achieve now and what will soon become possible. So the first point we basically put down is we can do population statistics now, and we've demonstrated we can do resolve studies as well with large representative samples. But what is that going to open up in terms of with Roman? How is that going to change? I think maybe it's a bit more of a given. We've talked about how we're going to get environments now, but is there any other points people can think of how this will sort of go to the next level?
I mean, some of this might go to Roman, and Roman will. Thank you.
And Roman would be fantastic for many things, but I think that the astronomy landscape also includes things like Prima in the far infrared, ALMA, and so on, and some of those things could actually lead to synergies there. So for example, looking for molecular gas and then connecting the cold gas that ALMA sees to other temperature, and you hear multi-phase molecular gas in this and that, and it's important to understand that physics to then understand the feedback, but then understand the galaxy evolution. So I think the synergies with what we're doing, HST, JWST, MIRI, and the whole landscape of surveys and facilities will be quite great.
Yeah.
I guess something I think of with Roman and what I've talked about, what I'm really excited is that depending on our science goals, of course, we have these very wide area ground surveys like SDSS and then pencil beam fields from Hubble. But now we'll be able to get it all from the same facility, the same filter. We won't have to deal with things like 0 points and resolution. If it all comes from the same facility, I feel like that can really cut down on systematic errors that are introduced by that kind of uncertainty.
And maybe the time spent on trying to like match PSFs and I don't know what when doing science or whatever. Yeah, no, that's a good point. Okay. You have something?
Yeah, you mentioned the result studies of large representative samples. So does that require like the forward modeling reduction of the Raman cyclic spectroscopic data? In a way, very similar to what Russell brought us with cyclic utils, for example. Like we would love to have an SDSS or manga size of galaxy sample at redshift 2, right? With 2 meter mirror diffraction limit and IFU quality data cube or pseudo data cube. But probably that is not equivalent to say only like 1D spectra for 100,000 or galaxies at redshift 2, right? That's we need like 100,000 data cubes at redshift 2. So is there like has there been archival efforts or planned investigation to reduce all the Raman spectroscopic cyclic spectroscopic data in a fashion very similar to like what we've seen from HST or JST nearest or NearCam?
So I think from my experience, it's more a worry than sort of like someone saying that we know we can do X. There are ideas out there of like how we can change how we process the data such that it is more rapid and it isn't so computer intensive. I don't know whether there is like one way we're saying, yeah, absolutely, we're going to be able to produce X amount of ridiculous amount of data cubes at the sort of, I don't know, grizzly level or something. So it's just not going to be feasible. And I think that's worrying because I don't know how you create something like that kind of data set. And, of course, people have thoughts on, whether there are ways, and they're very confident that that could be a thing in the future. Then, yeah, that would be good.
Yeah. This is a huge problem that we're thinking about right now. But so I have a Cycle 5 archival program to basically run my 2D code on all of the current public nearest and NearCam GRISM data. So it's sort of like a test case. Obviously, it's still not going to compare to Raman, but it's going to be build a database sort of with how we're going to process Raman in mind and how to do this massive data set. Raman's going to be daunting, but it's kind of a first order thing.
Yep.
To add, I think a number of people in the GRACE survey at least are thinking about this. And one of my goals in coming to this conference was to find out what others are doing in terms of software development and library development. So yeah, please mention your libraries in your talks and talk about the tools that you're developing, because this is really like a challenge that I don't think we're necessarily prepared very well for.
Okay, I guess putting that huge worry aside, we're going to the next point, which is MIRI WFSS, which was it was introduced today, and it's very exciting. And there's loads of capabilities for AGN science, possibly cosmic noon. And we were thinking, at least us three were thinking that this mode, especially in existing deep known fields can actually be quite powerful when combined with existing data. And this is something we can achieve now, as has been mentioned. And whether people have started thinking about that, some ideas that we can sort of bring the hive mind together.
There are some talks, there are 2 talks
on Wednesday
Mm-hmm.
By Sarah Kendrew and Roman. Sorry, I'm embarrassed. Roman Fernandez Aranda, who are going to present exactly that, some archival study for one of the well-known fields where we have everything in other wavelengths, and all you need is, so you know what you're looking at, you know your redshift, you know that's this bar and not that bar. So that stay tuned for that.
Awesome. Okay. Don't think any more thoughts on that, or okay, so the next point we thought about is this recent call for white papers for James Webb multi-cycle treasury programs. And that's something to maybe start thinking about in terms of what can we achieve now with that, or what can we make possible maybe. Whether anyone has any thoughts of that, so we can sort of start brainstorming regarding that.
My only highly crucial thought is that the papers are due November 15th, so there isn't a whole lot of time between here and there to get them done, especially if you're planning to propose for cycle 6. But now is the time to put those thoughts on the table. So, yeah, there are certainly folks who have a long head start on this, and there's certainly the rest of us who are well behind. But let's see if we can get that ironed out.
Okay, no more thoughts on that. Okay, I'm conscious of time. Do we only have 3 minutes? 1 minute? Okay, 27
3 minutes.
Okay.
3 minutes, 3 points.
Awesome. Okay, 3 minutes, 3 points. How should we approach the next generation of capabilities? We want to point out that the Euclid DR1 goes public in November, I believe. Correct me if that's wrong. Yeah, okay, Eva nodded, that's good. So we should think about that, because obviously it's another big wide survey, all sky, I believe, I don't remember. And think about using that with upcoming facilities to sort of enhance our science. Anyone have quick points on that? Maybe one person can say something, since we only have a minute per point. No? Okay, you lost your chance. Okay, next one. All Roman data will be public immediately. We're going to be flooded instantly with data, so competition will be different, or how we think of competition. And we need to start thinking about community efforts being more important. Anyone have anything on this? Yeah.
Can I just do a really quick PSA for Roman? If you're not already familiar, I just want to let you know regarding Jesline's point regarding time critical part of this. Roman will not use FITS files. Roman uses ASDIF files. So if you're not familiar what that means, you should probably, and you want to be on the forefront of this competition, you should probably get started now.
Does that mean we have to give up on DS9?
Right, so that means you sort of will have to give up DS9 to some extent. There are tools that the Institute has developed to sort of emulate some of that behavior. And we've got some tools on the Supernova team for easing your transition, but that's definitely worth being aware of if you want to be on the forefront of the Roman cycle 0 or cycle 1 data.
Okay, that's sufficient panic. That leads to the final point, which is the main panic. That's why it's in caps lock, is data challenge. We have a huge challenge. We have a volume challenge, and we also have a contamination calibration challenge. Visual inspections are going to be a thing of the past. Things of the past. So we need to start thinking of new ways of being able to quality check our data. Maybe this is where machine learning might help. I know we have talks later on in the conference, but we've hit the mark. But if anyone has any thoughts on that, they should speak about how we should worry/prepare for this. We have one person here.
So it's as a junior student, but there's one opinion that I think is that people might ignore is that we need a benchmark. Benchmark is super important when it comes to machine learning tasks. And for now, I don't see astronomy as a more unified and benchmark that people agree on. So, but I think it's a community work that needs a lot of input. So we can compare algorithm based on a shared benchmark. And maybe, for example, a set of visual inspections that with the spectrum and your results, and also maybe in the future for other tasks that what decisions that an experienced researcher would make. And we can extract those decision pairs and try to evaluate how algorithms or agent work on this. Yeah.
Anyone have any follow-up on things like benchmarks? I think it's important if anyone has ideas on that or not.
I think that's a really important point, and perhaps we should think about how we simulate data to create some benchmarks that would be useful, because we don't have the data yet, and by the time we have the data, that might be too late. In that view, I want to really underscore the fact that Euclid DR1 becomes public in the beginning of November, because the data will be very similar to what we will be getting from Roman, and especially the slitless spectroscopy will be reduced by IPAC with a pipeline that is very similar to the Euclid pipeline. So the outputs from that pipeline will be very similar. So even though the interface through which you're going to get the data from ESAC versus IPAC will be different, the data actually will be very similar. And that's going to be 2,000 square degrees and several millions of spectra, tens of millions of spectra. So this is the community that should really jump on this data before you start getting the fire hose of Roman early in 27.
Yeah, that's a good point. Eva, is Jatika, are you still here? I don't see her. Okay, so Jatika is a graduate student at Duke University working with Dan Skolnick, also but working with my group here at STSCI. And Jatika has led modifications to GalSim to do full PRISM simulations of the high latitude time domain survey with Roman. So those data are not yet public, but I think they are close to that. So they'll basically emulate level 2 images from before they go to IPAC. It'll be the things that IPAC would ingest. So if that's useful to you, come find me and I can work with Jatika to find you to get that.
Her talk is tomorrow at 9.
Yeah. And that's why I wanted to advertise her talk.
Okay, awesome. I think we've gone over time and I'm worried Andrea's going to tell me off, so I'll stop here. Thank you so much for getting involved with the discussion session, and I hope today was useful. I can also share.
Thank you so much to our discussion leaders for the great and insightful questions. So now, if you're interested in going to the unbanquet, make your way there. There is no time limit, but if you're there at 6, if we don't want, we have a reserved spot to get around. But again, it's it's a 25-minute walk, and the address is notes.
I'll be walking.
And he'll be walking. Just follow him. Yes, and ask for everything around us.
Yeah, I got it. I read it. I don't know if I have any more thoughts than what I said. I think
No.
it is possible.
I was talking to Andrea about a couple of things as well. So